Hey, hello again. Thank you for viewing this video. First up first. In this video, I'll be discussing mostly on uh, how to practically train a model, specifically a large model, not specifically a large language model. Um, and why am I making this video? Because these are kind of things which every industry wants from any engineer, right? Apparently, even if you're doing just inference of very large models, you need to know things on practical side of things, like how to actually do the inference of these kind of models. And it's very different from what we have learned in most of our courses, like running small models on maybe Google Colab or even locally. This is not how it's done when you join a company or industry. Uh, so these models are large, but how large? I mean, usually. So on the scale of things, what I'll be talking about, um, it can be treated as something like, let's say, from 175 billion to maybe 1 trillion, or even larger than that. And why? So what makes a model training, like a training of a model which is large, difficult or nearly impossible on local machines, or even variety of things to be worried about. It's not just the parameters. People say, we always learn about, like, GPT-3 175 billion parameters, GPT-4, I don't know howsoever many parameters, Megatron 1 trillion parameters, things like that. So we always hear about parameters, but it's not just the parameters. It's also about the memory. Parameters is a number, right? But what's the memory associated with the parameter? And where does this memory come from? The memory actually originates, just think of parameters as in, like, think in terms of like a feed-forward neural network. What would the parameter do? The parameter would actually go through a forward pass and a backward pass, subsequently saving some informations in the forward pass as well as backward pass. What information? Any information which actually facilitates the backprop, or actually facilitates the updation of the parameters, let's say. Why do we update the parameters? Very common answer. We need to find the best possible parameter which minimizes the loss function. Which loss function? The loss function which we set up. Depending upon your objective to train the network, you would have different loss functions. But ultimately, the thing is, depends on what you're doing: supervised learning, unsupervised learning, clustering, classification. I don't know what, but the essence of the thing is, you'll set up a mathematical problem, I would say, in a probabilistic way, and then find some parameters of your model which can minimize the loss function and give you the best result of your objective. I'm talking in general sense. That's why it's becoming a bit cumbersome to understand. Have I been talking in terms of, like, linear regression, fitting a line? You wanna minimize the residuals, and therefore you'll get a loss function like mean square error, and you need to minimize the loss function with respect to the weights, which in itself is the slope of the line and the bias as well, which is like the offset from the origin. In the sense of linear regression, it feels and looks pretty simple, but we have to be generalistic, right? It's not just all about fitting a linear regression. A neural network model is a generalist model. So it can do fitting a line, which is like prediction. It can do classification. It can do generation as well, which is like a hot topic these days. People generate variety of things. Some of the recent things are like generating videos. Okay, let's pivot and let's track back. So what I was saying, a model in true sense will require you to save certain things during the forward pass as well as the backward pass. These certain things, I don't know, maybe I'll cover it in a different video, but these are very basic stuff and very fundamental stuff of training a neural network, and what all is saved and where all it is saved. Is it the optimizer? Is it some cache which is saving something? And just don't worry about all that. You just think that a neural network is not just all about how many parameters are there. Parameters gives a sense of magnitude of the memory requirement which you would have during training, during inference, things like that. But in a sense, how would you train a model? A GPU, so let's say, so everybody, so we know deep learning, the advent of deep learning comes from use of GPUs. Why so? Because GPUs are absolute beast in doing calculations which are highly parallel, or which are overly parallel, let's say. So, I mean, there's an alternate term called embarrassingly parallel. These are all HPC terms. We don't need to worry about all this. We just need to know, okay, just some very simple example, dot product. A dot product can be done, let's say it's a vector of 10, it's a 10 cross 1 vector, and you're taking a dot product with another 10 cross 1 vector. So you can call 10 different processors to do that x1 plus x2. So x1, one processor, x2, one processor. Similarly, x10, the 10th processor, and then aggregate all this. You'll get the dot product. So just to give a brief introduction, why GPU and a deep learning model. So deep learning model is actually sets of matrix multiplication, and matrix multiplication is embarrassingly parallel, which means that it can be parallelized into various cores of the GPU or various nodes of the GPU. Now there are very GPU specific terms like cores, nodes, clusters, even a supercomputer. Like, what is a supercomputer? Is it just one node? Is it multiple nodes? Or okay, so we are not going to dwell into what are these specific terms, but I'm just gonna be saying that, okay, one GPU, that means it can do, like, let's say 10,000 calculations in parallel. So what would that mean? That means 10,000 cross 10,000 vector can be multiplied on a one GPU, exhausting its capability, let's say. Okay. So when you're loading a model on a GPU, it has got a particular cache memory, and that memory is actually used while calculating your forward passes, your backward passes, and so that memory can be used for that, as well as when you're loading your weights. So each weight or the number of parameters, so each weight, let's say in 16-bit or 32-bit, will be a number, right? Like weight is not just the way, right? Weight, it's actually a number. So whatever that number is, it has to be stored on a computer, right? So that during forward passes, you know which value to multiply to your previous layer activations or even the inputs. So that's one part. Again, it needs storage, but do you think 1 trillion parameter can even store like a 16-bit numbers, like 1 trillion 16-bit numbers? That is a lot, right? And modern GPUs, they don't have that much memory or like cache memory. Again, why so? GPUs are designed to not have that much cache memory because you can always have multiple GPUs. So having a lot of memory on one GPU will be more costly than having multiple GPUs with less memory. So it's all about the cost, right? It's all about the money, actually. Sorry. Yeah. So I'm nearing 10 minutes. So I think, oh, I can continue. Maybe I can continue. Yeah. Uh, so, so the thing which I was talking in the first part of the thing, in the first part of the video, was about more about what is the memory requirement exclusive of the memory requirement to store the weights. So I said it was not just about storing the weights, like that is the 1 trillion 16-bit or 32-bit numbers. Rather than that, it's more about what you store during forward passes and backward passes. And then I pivoted and then I said 1 trillion, then I just gave you a scale of things that 1 trillion parameters, again, it can't be stored on one GPU. So think about what will happen if you have the activations during the forward pass and backward pass. So it will overflow, right? It won't fit in one GPU in any sense. So you just can't train. Maybe you can load the 1 trillion parameters, but after loading the 1 trillion parameters, you definitely not gonna have any space left for training to storing any amount of cache. So what we do, we need to divide the model in a sense, like let's say we have multiple GPUs. So why not divide the model such that some layers of the model go into one GPU, subsequent other layers go into the other GPU, and so on. So does it make any sense? Yes, it does. Why? Because forward pass, backward pass goes on layer by layer, right? If you remember. So we can actually cluster the GPUs in series and have our layers set up in such a way that our data goes into one GPU, computes the forward pass on this one GPU, and then transfers everything which is required to the next GPU. And subsequently, it goes on and on and on. And then subsequently, the backward pass starts from the last GPU to the first GPU. But the problem is only one among the n GPUs is doing some work, right? The rest of the GPUs are like sitting idle. Well, that's not a good thing when you're training a model. And to just give you a scheme of things, GPT-3 is like 175 billion parameters, and it takes around 8,000 GPU hours to train the model. That means if it's trained on one GPU, which it may not be able to train, but if so, it trains on one GPU, then actually GPT-2 or 3, I'm getting confused, but one of these models can be trained on one GPU in a different kind of parallelism, which is called data parallelism way. So maybe the cost of training, the parameters, the size of the parameters and the memory requirement during forward pass and backward pass was under the limit of one GPU, so they may train. So let's say even if we are able to train on one GPU, it would take 8,000 GPU hours. You can do the maths and figure out that if we are having GPUs which are sitting idle and only one GPU is working for, let's say, 5 layers of the GPT model, then will it increase the number of GPU hours, and what will happen? So yeah, so from 30 days it would go on to 60 days and whatnot. So again, time, money, things like that. So it's 14 minutes, right? Okay, good. So these are some points which people should take care about during designing your training paradigm onto multiple GPUs. And the first method which I talked was that first few layers goes on one GPU, next few layers goes on another GPU. It's called model parallelism, but in actually in horizontal way. And it's also the other term which I think popularized by NVIDIA. It's called pipeline parallelism, or like so model parallelism has got two flavors, or like two methods of doing this. One is pipeline parallelism and the other one is tensor parallelism. So what is tensor parallelism? So yeah, very trivial. I mean, it's a naive answer, right? You have broken the model horizontally, right, layer by layer. Now break the model. You've broken the model vertically. So now break the model horizontally. That is, let's say there are 5 layers in the model. The top half of the weights of these 5 layers goes on one GPU. The bottom half of the weight of these 5 layers goes on the another GPU. Again, it may sound counterintuitive that how would the math work, but it works. For you to understand how the math works, I think I would need to go on Keynote and show the things like how it actually works. And it's not very difficult. Even anyone can do it, but it will be better to have it viewed on screen while understanding it. This video is not about getting to the depths of it, but just touching all the topics. Now comes so the two ways you understood, right? One is sequential way of breaking the layers. One is like a kind of tensor parallel way of breaking the layers. That is, each layer you can break into subsequent GPUs. And then comes the most popular way of training a model, which is fully sharded data parallel, or popularly called FSDP. What is FSDP? So FSDP is just a combination of both of these. That is serial level parallelism or pipeline parallelism, as well as tensor level parallelism. That is the vertical parallelism, that is like breaking each layer into 2 parts. And then another third way of parallelism, which is like the data parallelism. So FS and then DP. So DP is data parallelism. Data parallelism is very trivial. So I talked briefly about that, like how GPT was trained. So let's say if GPT was being able to, if the trainers of GPT were able to load that model on one GPU, then they can have multiple GPUs and then give divide the training data into batches, and each batch you create micro batches from each batch and give the micro batches to the separate GPUs. Do forward pass so that with the time of like one micro batch, you actually have a full batch, a full forward pass on a full batch. So that saves time, saves compute. Not actually, doesn't save compute, my bad, saves time. Yeah, and then subsequently do the backward pass and only aggregate the gradients from all these GPUs. That's what we do even in one GPU, right? We only do the backward pass after aggregating the gradients from all the samples within the batch, right? It may sound a bit tongue twisting, but if you just give some time, it will sink in. Don't worry. It's nearing 20 minutes. I need to finish. Okay. So what did I say? Yeah. So the most popular one is fully sharded data parallel. So what is sharding? Sharding is actually what I was talking about, like dividing the weights in a certain fashion. And I said it's a combination of both tensor parallelism as well as pipeline parallelism. But I did not say anything much more on how it is being done, because it's an involved process. It requires certain thinking, and it can be communicated like this. So I will definitely make more involved videos with presentations and all, and how gradients flow. But for now, over and out. Thank you. Hey, hello again. Thank you for viewing this video. First up first. In this video, I'll be discussing mostly on how to practically train a model, specifically a large model, not specifically a large language model. And why am I making this video? Because these are kind of things which every industry wants from any engineer, right? Apparently, even if you're doing just inference of very large models, you need to know things on practical side of things, like how to actually do the inference of these kind of models. And it's very different from what we have learned in most of our courses, like running small models on maybe Google Colab or even locally. This is not how it's done when you join a company or industry. So these models are large, but how large? I mean, usually, so on the scale of things, what I'll be talking about, it can be treated as something like, let's say, from 175 billion to maybe 1 trillion, or even larger than that. And why? So what makes a model training, like a training of a model which is large, difficult or nearly impossible on local machines, or even like local machines where some machines have GPUs, right? The thing is, even if you're able to fit in a large model on a single machine, which means fitting the weights of that large model, let's say 1 trillion parameter model or a Megatron. So that 1 trillion parameter model means that there'll be 1 trillion numbers, in the sense of like weights. What are weights? Weights are numbers, right? 1 trillion numbers represented in either in the 16-bit format or 32-bit format, floating point 16 or floating point 32, on a device. So they have to be written somewhere in the memory, in the cache memory, I don't know, but they need to be there during your training. And what else needs to be there? Yes, so a lot of other things are required during training. Those are called activations, gradients, and things around these two things, activation and gradients. There can be many things around activation and gradients, which you may already know if you have taken a deep learning course, or if you have ever trained a deep learning model and checked the optimizer state, the model state, or like try to print, or like try to do random stuff with the during training. So these things also need to be stored during forward pass and backward pass. So what is forward pass? What is forward pass and backward pass? Again, so training a deep learning model requires you to tune your weights such that the final loss function, or the loss function associated with your general objective, minimizes in this gradient descent fashion, or let's say in an iterative fashion. So these weights gonna align themselves in such a way that the final objective is achieved, let's say. What do I mean by final objective? So final objective can be very different in different settings. What are settings? So the settings are like supervised learning, unsupervised learning, generative modeling, and I don't know, supervised learning have got many paradigms, unsupervised have got many paradigms as well, reinforcement learning, things like that. So not to digress on all these things, I'm just saying that a lot needs to be saved in order to train a model, and the even the current state of the art GPUs are incapable of, I don't think they can even store 1 trillion weights, as in numbers of either floating point 13 or 16, 32 or 16 on their GPU. You can do a quick math of it, like what would a 16-bit floating point 16 number, how much memory it would take, and then multiply it with near about 1 trillion. It's obviously a model is not made like, okay, yeah, I want 1 trillion parameters, so it should be 1 trillion parameters. No, the models are not made like that. It's near about 1 trillion or something. Okay, so what you gonna do? I mean, plain and simple, we are not going to train anything, right? No. We need to train something. So the best way, the naive way, divide the model, start dividing the model. So what would that call? So that's a popular terminology these days. We call it model parallelism, right? So intuitively and naively, how can you parallelize a model? Plain and simple. Divide the model, cut the model. How would you cut the model? Thinking naively again, cut it layer by layer. Let's say we have like a model with 1000 CNN layers. So cut on the cut the first 100 layers, then the next 100 layers. So steps of 100. And then store these models in 10 GPUs. Pass in your data set sequentially, and then once the data set passes through all these GPUs, compute the gradients and compute the loss. These are there, but I'll take a pause in this video now.